Hey guys. All right, so last time we learned how to evaluate integrals using u substitution, but those were indefinite integrals. Today we're going to talk about what happens when we have definite integrals. So when we have, bounds from a to b. Well, in that case, right, if you have a situation like this, what you have to do is once you change your variable to u, you also have to go and you have to plug in your a bound into u, so you get a new number, u of a, and then you plug in b into the u, so you get a new value, u of b, and those will become the new bounds for the new expression containing u. All right, so let's do the first example here. In the beginning, everything is the same. First, you still have to decide what u is. In this case, the denominator is going to be our u, so x squared minus 4. And again, same process, du is going to be 2x dx, right? All right, so when we go over here, where did the u come from? It was underneath here. And then what do I have left over? I have x dx, which here, x dx is half du. Right, so here I put in half du, right? So ultimately what I have here is 1 over u du, and then the 1/2 in the outside. Okay, next what we're going to do is we're going to take each of these bounds, right, the 0 and the 1, and we're going to plug it into u here. So first the lower one, I say u of 0 is equal to 0 squared minus 4, negative 4. Then the 1, u of 1 is equal to 1 squared minus 4, negative 3. So now, instead of 0 and 1, my limits of integration are negative 4 and negative 3. So 0 and 1 were the limits of integration when we had the expression in terms of x, but now that we have a new expression in terms of u, our new limits of integration are negative 4 and negative 3. All right, next, same as before, I integrate. What's 1 over u du? That's ln of u. Remember, I have the half in front. And now I have limits of integration which go from negative 4 to negative 3, right? And now, same as before, I put in the negative 3, so I have 1/2 ln of negative 3 goes into the absolute value and becomes positive 3, minus ln of negative 4 goes into the absolute value and becomes positive 4. All right, so finally, this is half ln of, we never leave it like this, it should always be 3 over 4. All right, what's more, okay, is this 1/2. Sometimes it's brought back up as an exponent, so this will be, right, if this whole thing is raised to the power of 1/2, ln of root 3 over 2. Okay, right, because if you raise that up and make it an exponent, you will have ln of 3 over 4 to the 1/2, which is ln of root 3 over 2. Okay? All right, next. So that's number 1. Next, what I have here is tangent and then secant squared x. All right, so here, your first instinct might be, okay, I have a secant squared x, so u should be secant of x, right? But if you do that and you try to do the integration, you will see that, the derivative of secant will be secant x tangent x, and then once you substitute there won't be enough for you to close everything out. Or you might also notice that, hey, wait a minute, if I pick u to be tangent of x, its derivative, du, is secant squared x dx, and that fits a lot better. All right, so I substitute now, and I get that tangent is u, secant squared dx is du. And now I need my new limits of integration. I put 0 into u, so I get u of 0 is tangent of 0, which is 0. U of pi over 3 is tangent of pi over 3, which is root 3. So instead of 0 and pi over 3, I now have 0 and root 3. And then when I integrate, I have u squared over 2 from 0 to root 3. Look at what happened here. When my integrand was in trig form, right? It was trig functions. My limits were in radian. But when I switched and my integrand is now just a u, which is an algebraic function, my limits also changed and they're no longer in radian, right? They're just regular numbers. All right, so let's put in the root 3 and I get 3 over 2 minus 0. That's just 3 over 2. Okay, last but not least, here's what I have next. All right, so this is a little bit of a different situation in that I have a 9 and a 9 plus x squared on the bottom. So for ones like this, we just sort of have to do a little trick. And at first, you're going to be asking, oh my gosh, how was I ever supposed to know how to do that? And the answer is you weren't supposed to. But now that I tell you, your eye will just be trained to recognize integrands of this form, and you'll be able to do this trick. So you see how there is a 9 on top and a 9 on the bottom. What we're going to do here is we're going to we're going to multiply the numerator and the denominator of this by 1 over 9. Why, you say? Well, I will tell you. Because when I do this, right, now I get the integral from 0 to 3, 1 over 9 times 9, it's just 1, so I just have dx, over, when I distribute this, I now have 1 plus 1 over 9 x squared, which is x squared over 9. What's more, I can rewrite that further as 1 plus, not x squared over 9, but x over 3 squared. Okay, what did that do? Well, here's what it did. Now, I can say u is x over 3. So du is 1 over 3 dx. Okay, so when I go and I try to substitute this back in here, look at what I have. I have 1 over 1 plus u squared. Okay, and then what's the dx? It's 3 du. Okay, so 3 du. Oh my goodness, look at what happened. Isn't that inverse tangent 1 over 1 plus u squared? It so is inverse tangent, right? So these are like, little hand tricks that we do, but they're very common. And you see this form a lot where you have a number over the same number plus x squared. All right, let's substitute our u's. U of 0 is 0 over 3, 0. U of 3 is 3 over 3, 1. So here I'm going from 0 to 1. Okay, and so now when I integrate this, I'm going to have 3 inverse tangent of u from 0 to 1. So that's 3 inverse tangent of 1 minus inverse tangent of 0, and that will be 3 times pi over 4 minus 0. So that's 3 pi over 4. All right, and that is that. And now you can go ahead and do your the rest of your worksheet. All right, I will see you guys soon.